My video building and testing this BasenGreen battery has over 1 million views, and I've been cycling it for months now with not a single issue. Now they've sent me version 2 to build and test for you, and it's only $30 more than version 1. Plus, you get some really nice upgrades, including a physical breaker and active balancing. I wasn't a huge fan of building DIY batteries from scratch because there wasn't enough cost savings to warrant the effort, complexity, and added risk of a fully DIY build. But I like this middle ground, where you get a case and all of the components you need to assemble it yourself. I can use the cells that I want, make sure the entire thing is built properly, and I get a significant savings with a professional result. This version 2 case is only $468. And these 314 amp hour grade A EVE cells are only $50 each, including an estimated shipping for most people of about $493. That's a 16 kilowatt hour battery for only $1,761, or $110 per kilowatt hour. That is really cheap. The US stock pricing is a little bit different, and I'll link to that option once it's available. I don't currently have an affiliate program with them, so I don't get anything if you buy one, although that may change at some point. So I'll show you my build and testing, and you can decide if it's right for you. Welcome back to Projects with Everyday Dave. Let's get started. One thing I like about BasenGreen is they put an insulator on the lid. If there's ever significant damage to the lid, you can't contact any live surface directly with the metal lid. I think that's a great application. The first thing we have to do is take the PCB boards out. Then I can remove all the components that are shipped inside. Here's one improvement, a lot nicer adhesive on the PCB boards where the wires come in. Looks like the insulation has not gone beyond the edge of the ring, so that should be good. They've already applied the backing, and this is much thicker than in the past. Really heavy insulation on the back side of these. That should capture the cells a little better as well. Here's all the insulators that go around and in between the cells. Some reinforcing brackets. Then here's the rest of the wires and hardware. EV foam to help space out the batteries, additional wiring harnesses, communications cables, terminal covers, additional bolts, the nuts for the batteries, and finally, flexible bus bars. And I really like the flexible bus bars. Now, these don't have an additional mount for the sensing wires, so you have to put it in with the terminal. Additional mount is nice, but as long as you torque everything down, it should be okay. Working on this table makes it a lot easier to get the screws from the underside. Now you can see we have a separate balancer, and that's why we have the separate set of cables here. This is an independent cell balancing board, and then this is the BMS, and here is a nice massive breaker. Do a little inspection here and make sure everything is in good shape. These are torqued down without any insulation under them. That looks good. However, here on the breaker, it looks like some insulation has been trapped. I don't know if you can see that, but there's a tiny bit of insulation trapped under that screw. So I'm gonna have to disconnect all of these and trim the insulation back and reconnect them. And that's one reason why it's nice to do a build yourself. You can make sure that everything is correct. If you just bought this battery built, it's not like you're gonna open it up and check all the connections, but when you build it yourself, you can do that. And I can tell you, I've had batteries built from a manufacturer that weren't operating right, and when I opened them up, things weren't properly torqued, insulation was under terminals. So in some ways, I think sometimes a DIY battery can be better. Now that I remove it, I can see that the insulation is behind the flat, so probably that was okay. But just to be sure, cut that back. Now I know that there's no problem. I need to be sure and torque that back down. I'll torque it to 8 Newton meters. This one also just makes me a little nervous. Oh. And check that out. This isn't even finger tight. That one is, but this one isn't. Wow. There's no quality control paint marker on these showing they've been torqued. So it's your responsibility to go back and make sure these main things are torqued properly. And we're gonna do these to 8 Newton meters after I trim the insulation off. You can see this has insulation up onto the flat. That's no good. Trim that off. Now this can be a little bit harder to get to. I need an Allen wrench to get inside there. Wow, that was definitely torqued. That was tight. All right, yeah. I mean, I can clearly see there was insulation under that. And that's no good, you don't want that. You can see the insulation marked there where it was crimped down, and that prevents it from seating completely, and you'll have a chance of a high resistance connection there. So we'll cut that back. There's no need for the insulation to go all the way down like that. Just make sure the entire flat is free from insulation. Clean this one up too. There we go, we can put this back together. Now we're good and safe. You see a little bit of metal, we'll clear that. I can be confident we're not trapping any insulation under the contact. There we go. I checked these, they're good. All the insulation problems are fixed, everything's torqued down, so we can set this aside and put the rest of the battery together. All right, finally we just need to remove the compression plate. There we go. Just like before, really nice solid construction. Everything's powder coated on the inside. The brackets are welded in. There's a center frame down the middle we'll use for compression and stabilization. Looks really good, no problems there. Before you get started, make sure you take off any jewelry, and it doesn't hurt to put on some rubber-lined gloves if you want to add a little extra protection. BasenGreen included a very nice color assembly manual, and it's pretty easy to follow. For today's build, we're using EVE 314 amp hour cells that I got through BasenGreen. And for the first time, I did have a problem with the shipping of one of these cells. And I tell you what, I feel like the shipping industry is just getting worse and worse all the time. I don't know if they put all the packages in a tumbling machine before they bring them over, but man, it's been terrible lately. This one looks like it got hit with a forklift, knocking a big chunk in the side of the box. And these are packed really well with heavy duty, thick foam all the way around, completely encasing these cells from top to bottom. And it went through the box, through the foam, and dented the side of the cell. Now I did run a capacity test on it. These cells test 327 amp hours, which is well above the rated capacity. This cell was 324 amp hours, which is 0.09% less than the undamaged cell. And maybe it would be fine, but I don't think you want to take any kind of risk with this kind of a setup. So I went ahead and asked them to replace the damaged cell. Unfortunately, they don't currently have a method to send just one cell, so that added some complexity. I think it would be a good idea for them to have a package that has just one cell in it for situations like this. Or maybe it's so infrequent it's not a big deal, but if you do run into a situation where you have a damaged cell, I wouldn't use it. I would get a replacement cell. So now that the new cells have finally come in, we can put this thing together. I like to place all the cells ahead of time in the order that they're going to go into the case, so I make sure I don't mess it up. And then I confirm at the end to make sure they're all correct. And I'll put the pattern up here on the screen. It's in the manual, so you'll know exactly how to place them. The first step is to put the insulators into the case. That protects the cells all the way around from any metal-to-metal contact. And then one in the back. Then there's 4 pieces of EVA foam, so I'll put one at the back of each stack and one at the front of each stack. And then we'll just place all the cells in. Between each cell goes another insulator. We'll put in our final piece, our EVA foam. Now I can put the compression plate on. I'll make sure that there's no material blocking the assembly. There's a very small gap there, so the bolts will pull in and pull that tight, and everything will be nice and snug. The cells are not super rigid. Like I can move them, but they're snug, they're not going to rattle around. This isn't applying any significant amount of compression, it's more of containment. Most of the balance leads are okay, but there's a couple of them where the insulation is just a little too far up on the eyelet there. A good way to check is to just put the nut over it, and if the nut is covering the insulation, then you know it needs to be trimmed back a little bit. So I'll go ahead and fix, I want to make sure that there's no insulation in my joints. Now the cables for the BMS have this really nice, heavy-duty, flexible shield over the wires, but the balance leads for the active balancer don't have any protection. The harness comes right across the sharp edge of this case, and since this is in a house, there's not going to be a lot of vibration, but that's just not a good practice. So I have some corrugated tubing here I can put over the wire harness to make sure that it can never wear through. I've had a lot of people ask in the comments about using these batteries in an RV, and you know, it's not designed for that kind of use case, but it is really robust and well built. If you were going to use it for something like that, you would definitely want to do some extra effort to protect the wires and stabilize the wires in the case. Every cable and every wire that's loose and can move around has the opportunity to rub against something and eventually make contact through the sheathing. So add protection to the cables and secure the cables within the case and on the top if you're going to use it in a place where it could see some vibration. All right, with the cells in place, we can now set these bus bars, nice flexible bus bars. There's a diagram in the manual that shows you exactly where they go. The end result should be we have a positive and a negative terminal at the end that are left open, and the rest we're going to connect in series, so it's pretty simple. I like to leave the last one that connects the two banks open and put it in towards the end. That cuts the voltage I'm exposed to in half. Make sure to put the correct board on the correct side. The PCB1 board goes on the right side, and the PCB2 board goes on the left side. Make sure no wires are trapped underneath, and then we'll torque those down to 6 Newton meters. Now there'll be a sensing wire on each one of these bus bars and a balancing wire. So the instructions show exactly which one goes in which place, but basically we'll need one sensing wire for each side of the battery and one balancing wire. I can set all of those nuts, and I kind of like the fact that there's not a lot of extra wire there. It can't rub or touch on anything. All right, it's time to wire the active balancer. I added some corrugated tubing there to make sure we don't have any contact with that sharp edge. Do not plug these into the active balancer before we have all of the rest of the leads connected and we can confirm that the voltages are correct. Because if you do it in the other order, you'll get some magic smoke like I got here. And then you'll have to replace the active balancer. So before we plug these in, we'll make all the connections. In addition to that, I've actually labeled all of the bus bars B1 through B15, and that matches the labels on the cables. You can get that information out of the manual. It tells you exactly which one is which label. That'll just help make sure I don't connect anything incorrectly. So I can start with B1. First wire on here is B negative, which will go to the negative post. We don't need that one yet. B1, B2, B3, and so on until we have them all temp set. B8 will go here. I'll connect that one last. B11 is red. Then we get into the second harness, 12 and B15. Now I'll go ahead and put in my connecting bus bar, last one here, and B8. Now I'll set my torque wrench to 6 Newton meters. There we go. I'll go ahead and torque these down row by row, making sure there's no insulation under them. Now before I go any further, let me just check the pack voltage. Should be a little over 52 volts, 52.15. That's a good indication that we've connected it properly. Now before I connect these cables up, I'm going to go ahead and connect the BMS and the main power connections, and then we'll plug in the balance leads. Before I plug this into the BMS, I can connect it to the PCB boards and check the voltage across the terminals just to double check. Between the ground and the last one, 3.2 volt. We should work our way up. 6.5, 9, 13, 16, 19, 22, 26, 29, 32, 35, 39, 42, 45, 49. Why is that 21 millivolts? Oh, it's not connected. And 52. There we go. So now I know that these are all properly connected. It's very important that those are connected properly. Otherwise, we'll have a problem ruining our BMS. So now I can plug the other end of this cable into the BMS to make it easier to assemble. There we go. Disconnected the power cable and connected that up top. Get our temperature sensors up here out of the way. Put the face on, and we can make those connections. All right, first we'll connect the positive. 3 connections here. We have the BMS management wire, the active balancer wire, and the main positive terminal. Okay. All right, now I need to put the negative on the negative post under this wire on as well. And we also need the active balancer negative. It says right here B minus. I don't like how that one's coming across, so I'm gonna loosen that up, bring this in a little tighter. There we go. All right, so that's wired. That's wired. I can plug in balance leads. Okay, now even before I plug in the active balancer, power's off, but power to the BMS is connected before the breaker. So we should be able to turn on the BMS. Actually, I want to be able to turn on the BMS even when the breaker's off. So I'm going to move the power wire to the battery terminal. And that's totally up to you, but I have that feature on other batteries and I prefer it. way I can mess with the BMS settings without it being connected to the system. So I'm going to add one more wire to this main terminal. A lot of wires going on there. Make sure that none of them has insulation under them. Or gloves pinched in it. Now I can plug in the BMS. We should be able to turn it on now, even with the breaker off. I've been building these batteries on the floor because they're so heavy, but I'm getting too old to be bent over all the time. So today I'm trying out this industrial grade E7 Plus standing desk as an adjustable workbench supplied by the sponsor of this video, FlexiSpot. You can choose one of many desk options like this dark bamboo, but if you're into DIY like I am, a great option is to order just the powered frame and build your own top. My son is working on his degree in industrial design and needs an upgrade from his current desk that we built out of pallet wood. For a unique look, we're building this custom desktop out of some scrap black walnut and ash that we had in the shop. I use projects to justify all my tools, so we built a router sled to flatten the desktop. With its 440-pound lifting power, it can easily lift both of us and this heavy 5-foot wide solid wood desktop to its full 51.6-inch height with no issues. Now that I've seen a real desk, I regret buying this cheap two-legged one off of Amazon. It's so wobbly, just typing on the keyboard makes the monitor shake. I can't even lean on it without bending the whole top. The E7 4 Plus is a great value compared to comparable four-leg desks. FlexiSpot is having a mega sale now, so don't miss out on the chance to get your own E7 Plus four-leg standing desk. If you have a limited budget, you can choose their E7 Premium desk. Use my discount code in the description below for an additional $50 off. FlexiSpot also offers special discounts to military, students, doctors, and more. Click the link below. You won't be disappointed. Now, let's finish assembling this battery. Moment of truth. Look at that. Powered right up. It says state of charge 60%. That's probably about right. All right, BMS works. We have power. We can plug in those balancing leads. Oh, we gotta put our temperature sensors in there. Get this thing closed up. Now I can plug in the active balancer, the two active balancer cables, and I've run the temperature sensors, one down inside the front, one down at the back, one at the middle on the left bank, and one at the middle on the right bank. I use some zip ties to try and manage the wires. The one thing I don't like about the separate active balancer is it adds a whole lot of extra wires that aren't well managed. Without these, you just have a nice board with a sensing wire dropped at each station. And the JK BMS has the active balancer built in, so you don't need these extra wires. And you control the voltage at which the active balancer will run. But at least it has an active balancer. The BMS is on and running. All the wiring is done. Let's put the lid on and do some testing. I've connected this battery using 2-aught DC cables. I'm using a regular Ethernet cable for communications to the battery port, and I'm connecting the ground wire to our ground bus here to bond the case to the rest of the system. At the battery end, my 2-aught cables are just coming into the plus and minus, and then the communication cable I have connected to the CAN port. For the BMS, I have the dip switches all in the off position for battery 0, since this is the one that's communicating. If you have other batteries connected in parallel, then you would set the dip switches for those batteries to 1, 2, 3, etc. In the BMS menu, I'm using the Pylon communication protocol for both CAN and RS485, but I'm connecting the Ethernet cable to the CAN port on the BMS. The EG4 12K PV and the 18K PV settings should be the same. If you want communication, use the lithium battery setting with the communication protocol number 2 for Pylon. That worked great for me. If you don't want communication, you can select the user mode, which is called lead acid, and just control everything by voltage, which I like to do anyway. You can combine communication for visibility of the state of charge and still use voltage to control the charging. And that can actually give you a little bit more control, since state of charge can drift over time if you don't charge it to 100% on a regular basis. So let's review those settings. Here is a chart of the voltage settings that I like to use to maximize battery life. At the battery cell level, we want to set the BMS to the cell limits because the BMS is there to protect the battery from overcharge or over-discharge without interfering with the day-to-day operation. This chart combines the battery specs for reference with my actual settings on the inverter. The cell column is the value for an individual cell, and the battery column is just the cell column times 16 for the entire assembly, since all of those cells are in series. The spec sheet calls out an end of charge voltage of 3.65 volts, which should be the maximum voltage in the BMS. For the battery pack, this is the absorb voltage, and I'll set that to 56.2 volts, which is equivalent to about 3.5 volts at the cell level. On the battery charging curve, you can see that this is well above the flat part of the charge curve to allow for balancing. Then I set the float voltage to 54 volts to prevent it from constantly running a charge cycle. Now we use the end of discharge voltage from our chart. The BMS should be set to the minimum of 2.5 volts, but you can see that there's no real capacity left past about 3 volts. So I can set the pack minimum at 48 volts to reduce the stress on the battery and still use the majority of the battery capacity. After charging and discharging the battery with those more narrow voltage settings, I applied a 4,000 watt load and I had a usable capacity of 13.5 kilowatt hours. Of course, if I lowered the load or expanded the voltage ranges, we would get the full 16.8 kilowatt hours. But this shows a practical worst case with those limited settings. To confirm that true max capacity, I ran a capacity test on the individual 314 amp cells that BasenGreen sent me for this build. They are EVE 314 amp hour MB31 lithium iron phosphate cells, and the results were very good. You can see from this chart, I charged the battery to 3.65 volts, let it sit for 30 minutes, then discharged it at 40 amps down to 2.5 volts, and that resulted in a capacity of 327.2 amp hours, well over the 314 amp hour rating. After the capacity test, I charged the cell back up to 3.31 volts to match the rest of the cells for assembly. That's over 1 kilowatt hour per cell, or 16.8 kilowatt hours for the whole pack if you use the full range of the voltage. All right, I want to push this thing to its maximum 200 amp output, or 10,000 watts, and my EG4 12K PV can only pull 8,000 watts. I'll connect my EV, that'll pull 8,000 watts, and then I've run an extra set of cables here over to my Victron system, and I'll pull another 2,000 watts plus out of that, so we can get a full 10,000 watts out of this. To measure that, I've connected both inverters through my Victron shunt to this battery. So this negative cable here will see the full 10,000 watts. We'll see a little difference in heat between the cables, the ones carrying the full 10,000 and the ones carrying 8 to 2,000. Then I'll pop the cover off, we'll use my infrared camera, and I'll see if there's any hot spots in there. So let's push this thing. All right, the EV's plugged in and I'm pushing a little over 8,000 watts that direction. Now, let's pull some from the Victron side. I'll filter it out a little bit, but you can hear the fans howling in the background here. That thing's pretty much maxed out. All right, now we'll start pulling from this side. Oops, went the wrong way. Pushed 1,000 watts instead of pulling it. All right, let's see. All right, there we are, 9,000 watts, 180 amps. BMS is still rolling. Let's go all the way to 10,000 watts. Ooh, there we are. 10,000 watts, 200 amps. Let's check the BasenGreen BMS and see. It's probably showing a little more than that because we're measuring outside of the battery. We're going to run that for a little bit and we're going to check it with the infrared camera and see what it looks like. Well, it's showing a little over 200 amps as well. That's great. So this is slightly over the maximum output. I don't know how long it'll let it run. I'm sure there'll be some limits on that. So let's get the infrared camera out and see what it's looking like while it's at its limit. I'm going to back it down just a tiny bit so we don't trip the BMS before we can measure all the heat levels. I hear the BMS beeping. I wasn't fast enough. All right, the BMS gave up. So we were running 210 plus amps there for quite a while. There's going to be a limit in the software that doesn't let it do that for very long so that it doesn't overheat things. So I'm going to have to run it just under 200 amps so we can see if there's any hot spots in here. But we ran it over its maximum 200 amps at about 210 plus amps for several minutes. I'll put the total amount of time here on the screen before the BMS stopped that activity. So let's try one more time just under 200 amps. All right, we're at 193 amps, 9,940 watts. I think that's pretty good. Let's see how things are running here. All right, the battery pack itself looks totally cold. It's about room temperature. It's 90 some degrees in here, so no hot spots on any of our battery connections, so that's really good. Then where all the power's going out here. Got about 150 Fahrenheit there on the input and output to the breaker. The bus bar is cold. Nothing crazy hot down there on the BMS. That all looks pretty good. Now you can see the difference here in these cables. The cable carrying 10,000 watts is about 130 degrees. And then it's split off into the two inverters there. The hotter one, just over 100 degrees, is probably carrying 8,000 watts, and then that cooler one's carrying 2,000 watts. Well, that gives you a pretty good idea of what this battery can do. If you have an 8,000 watt inverter, one battery should be no problem. If you have a 10,000 watt inverter, you're going to be bouncing against the limit. You might want to get two batteries. The breaker's fairly warm, and I mean, you're going to have that with a breaker. They're designed to be tripped by heat, so it has to get warmer as you get closer to its limit, and it's a 200 amp breaker, so we're running right at its limit. The rest of the battery and all of its connections are super cool, no problem. I'm pretty happy with that performance. Everything's within a tolerable limit, right at its 10,000 watt max. I'm going to let this run for a while at its max and see if we have any issues. All right, we've been running this thing for over 30 minutes now, between 9,000 and 10,000 watts, really close to its maximum. And you can see the breaker's starting to get pretty warm. It's 190 degrees Fahrenheit. The one cable carrying the most load there is maxed out. It seems it's saturated at 180 degrees or so. But everything else in the battery looks really good. I mean, it's just barely over room temperature. It's almost 90 degrees in my garage, so the terminals are nice and cool. You see the heat sink on the BMS there is getting pretty warm, but I mean, we've been running at its max. That's what you'd expect. And it has thermocouples in it that'll shut it off if it gets too warm. So I think that's pretty good. It's meeting what it says it can do. I really like the upgrades that come with version 2 of this battery. I like being able to keep the BMS on while physically disconnecting the battery with the breaker. The addition of the equalizer is nice. Although it adds some complex wiring, you can always disconnect it if you don't want to use it. Overall, it's a nice upgrade from version 1 and a great option overall for the semi-DIY battery space. Plus, it's a really great price. If you combine this battery with a 3 kilowatt solar array, you can run a fridge, lights, well, and emergency systems pretty much year-round without any problem. As usual, I'll leave links for the battery and any other discounts I can offer in the description below and on my website, projectswithdave.com. On my website, you can also find lots of other helpful calculators and resources that will help you in your solar projects. Watch this video right here for more on the performance of the EG4 12K PV that I used to test this battery. Or watch this video right here for more on batteries. Thanks for watching, and I'll see you next time.